Alright, Assalamualaikum warahmatullahi wabarakatuh. We are on chapter 5, which on the textbook itself display as topic number 6. So this topic, we have three main components. Number one is to define what it meant by momentum and impulse, and then to employ an expression where we call it conservation of momentum. This is really quite similar to the concept of conservation of energy. And finally, applying the two concepts together of 6.1 and 6.2 into a situation called collision in one dimension. That's it. Okay, so let's start with what is a momentum, right? And what is impulse, and then we combine them together. So what is momentum? Momentum is a product where a product of mass times with the velocity. Okay, and my concern is, bear in mind that it had to be a velocity. Hence, this is a vector product. Vector product. You had to be alert on the direction of the V itself. Okay, and therefore, you will find that the unit is consistent with the product of mass kilogram and as well the product of V meter per second. So it becomes kilogram meter per second, right? So, in general terms, when we say object has big momentum as compared to another, I give you a situation. So, how hard an object can be stopped when it's moving? Okay. So, as an analogy or as an example, you have a motorcycle and as well a bicycle, or perhaps a car as compared to a motorcycle that travel with the same amount of V. Speed dia sama, velocity dia sama, moving in the same direction. So what makes them different would be mass. And therefore, which one is harder to stop is the one having bigger momentum. That will be the car, because of the momentum. Mass of the car is definitely bigger than a motorcycle. As simple as that. Right? So that one way of portraying concept. What is momentum? Now, so basically, let's look to the next page. We find as well when we go over the concept of Newton's law as portrayed by the books over here, that force is equivalent to ma, and then we expand the value of acceleration to be a rate of change of velocity, and then we combine them together, mass and change of the velocity. You find that this expression become a momentum, but together with the term change of the momentum. So this delta is change. This delta is change. So in short, when we rearrange the expressions, it's becoming from here to becomes over here. The change of momentum over time interval, or sometimes we call it rate of change in momentum, is as well equivalent to the product of force exerted on an object, okay, or net force exerted on an object. Now, this expression, what they did is they rearrange it. How did they rearrange it? Now, the delta T is transferred to the other side together with the force, becoming force times delta T, and leaving only change of momentum on the left parts. Okay, so from here we get to this expression. Okay, so this expression shows that the product of change in the momentum is equivalent to the product of force times delta T. And force times delta T get us to a second concept, what we call as earlier on momentum. And our next one now is definition of what is impulse. So impulse is a product of force times T, okay, a constant force that acts on an object delivered over a time interval. It's called as an impulse. Now, observe over here that impulse, which denotes by the expression I, by the symbol of I, is as equal to the product of change of momentum. So earlier on, momentum individually has the unit of kilogram meter per second. And that's the reason that impulse as well would be having the same unit, which kilogram meter per second as well, or you can choose to write down as similar to individual equation over here. Force being Newton and time being second. So Newton second is actually equivalent to kilogram meter per second. Now, getting to impulse momentum theorem over here, when we say it's theorem, the treatment or how we approach a question mean that request us to make use of the equation straightforward. We just use that expression as simple as that. But the key of this expression is that, or we say is the key or technique or gateway lah, or we say is tips, okay, that we are definitely using this expression gonna be when we observe there is a change of the velocity, means that the u and v are different in value. And perhaps in the question, it's really like to know what will be the force exerted on the system when the system or even the object experiencing change in the product of u and v. Alright, now before we proceed with the calculation, I'm going to show you something, okay? So look closely, you're going to see something which has similarity to work energy theorem, okay? Whereby force we're going to open as MA, T is delta T, and over here M V final minus U, or you can even write down as equation impulse momentum itself. Now I cancel out the product of mass, okay? And then we have A, rearrange it as V minus U over delta T, where voila, you get change of velocity, rate of change in the velocity, okay, is equivalent to the acceleration. Notice something as you make comparison with work energy theorem. Yes, the two equation actually comes back, rooted back to what we call kinematic expression. The only difference is the work energy theorem is rooted with the equation associated with displacement. However, for impulse momentum, it's getting or rooting coming back to the kinematic expression that correlates with time. Okay, now let's look at a few things more. Okay, now this is a figure or analysis when associated with force and time. Recall that whenever you have a graph, force versus time, and therefore the area under the curve will be a product of force time delta t itself. Means that the area is now equal to the product of impulse. Area is as well equivalent to change of momentum. Either, both are the same. Okay, so which area that we are talking about? The shaded area. However, okay, in a scenario whereby the force is, you can see in the original expression earlier, the force is denotes as F, just a single value of F. But as we can observe in the picture or the graph over here, the value of the force are increasing and later on decreasing. So in short, they are not of the same value. Dia tak constant, dia tak sama. They are changes with time. And then how is it that we're going to employ that is becoming impulse momentum theorem? Okay, so for this scenario, it's very interesting to know that in the case whereby collision occur as given in the figure, example given in the figure, whereby a bullet penetrates because of the collision with an apples, okay, so the keywords is collision, and due to that the speed changes, okay, and you have noticed that this process occurred in a very short time. Turns out when the time is very small, very small, okay, you find that the average force, okay, the average means that if this is 100, this is 50, okay. If here is 80, then we are talking about 40 as the average. Turns out that the area shaded over here is as equivalent to the area shaded under the curve graph. Okay, this is very interesting because makes sense then. Okay, because of that, then it makes sense that you can still opt to choose to calculate by using this expression of force time T. So writing style can be FAV, or you can even write it down as F with an average over here, delta T, and then change of the momentum. So in conclusion, even though the force is varied over time, okay, in the case of the collision, you find that you can still opt to use the expression because the force is still equivalent as if we are taking the force average. So there are two scenarios, there are two core concepts that I just mentioned just now. Number one, the area under the curve is equivalent to impulse. The area under the curve is also equivalent to the change of momentum. But on a side notes that even though the force is varied, because the time is actually very short in the case of the collision, and the average force is actually equivalent to the product of time delta t, and the area is equivalent to the product of the varying force earlier. Right. So another thing to note in the case of brain boxing and brain injury, this is a concept of padded. So you have noticed that if we are considering force time t impulse earlier, when we have padded situation, the time would be larger as compared if it's non-padded. Then when it is non-padded, means that time would be much shorter. So when time is much shorter, the force exerted on the object or whatever being collides on will be much larger. So in this case, we wear padded glove is because to increase the time. Okay. And of course, I leave you with the terms roll with the punch to give it another reading to understand the concept. Alright, let's have a look at this example. I'm going to choose to discuss only 6.2. Okay, so let's just look. Okay, we are going to discuss everything. Okay, so what is this example? We have a picture shows you over here a car traveling to the left and then later on collide with a static wall and somehow rebound in the opposite direction. Rebound ni maksudnya dia move in opposite direction ya. Therefore, in our calculation of this exercise after this, we are going to observe the concept of momentum considering that is a vector product. So, what is the story? So, in a car crash test, a car of mass 1,500 kilogram, it collides with a wall and then later on rebound. So, remember the term rebound is velocity is now in opposite direction. So clearly the question shows you the direction on the velocity itself, negative, and later on positive. So the initial velocity and final velocities, okay, the terms are properly put down over here, means that the data will be given together with the direction. Sometimes the questions are not giving you the direction. So it will say something, the initial and final speed of the car respectively are something like that. So you have to be careful when it mentioning speed. So if the collision lasts for 0.15 second, find the impulse delivered. Okay, so by right we understand that impulse is the product of force time delta t. But however in the calculation there's no force, but time did given. Okay, so here required you to step up your games a little bit, whereby you had to remember that impulse is as well equivalent to the change of the momentum. And with that in mind, what we did is, so you go by the expression of mass. So just, even though we are writing it as impulse, but bear in mind impulse is as well equivalent to change of momentum. And therefore, we can step up with V final equivalent to positive, 2.6. Initial is minus 1.5. So it becoming something like this with mass 1,500. So you should be arriving with this answer. And it's as well correct to choose another unit, which would be Newton second. So as simple as that. Okay, or even choose individual calculation of momentum initial, momentum final, and then getting it into final minus initial. Otherwise, you can even choose the one that I write down earlier. B final minus U. Alright. Okay, so getting that as the answer. Now, B, magnitudes. Magnitudes meant for value and direction. Okay, so magnitudes, here goes. Now that you have impulse, okay, so the value of the impulse at the same time, even though expression is going to be equivalent to change of momentum, Remember earlier I did mention FT, so the question is now asking you what would be the average force. And simple as the shown calculation, just divide with the time taken. Now, getting with 3 decimal places, they want you to make sure that at least you consider in your calculation 3 decimal places before you arrive with your final answer. And that's how you arrive with the value of the force. Okay. Now, in terms of the direction, it's very simple. Okay. It should be equivalent to whatever you have substituted. So, since we are substituting expression, mass, and then velocity belongings to the car itself, mass and velocity belongings to the car, and we, by right, with respect with that, we should arrive with the force together with the direction on the car itself. Okay. Now, in our next section, we are going to discuss when we have here wall and as well car. So, how we do approach the concept of Newton's law. Okay. So, right, stay tuned for our next one.